Welcome back, CIS 1400. Hopefully you're coming to this video from watching the previous video on arrays and Python lists in general. Today, in this particular video, I want to walk you through how we can manipulate that basic data structure to be used in a deeper way. So we're going to talk about how we can embellish it quite a bit. So let's get into it. First thing I want to introduce you to is this idea of parallel arrays. So an array is meant to be a data structure that has data, but all of one particular type. And sometimes we have lots of information that we have to go to, and all of these pieces of information reference one particular thing, but the information is of different data types, so they don't quite belong in the same array. So what we can do is set up separate arrays or separate lists in which the indices correlate between objects. So here in the example here, I have two different lists or arrays here, one called names and one called numbers. Names is obviously going to hold a bunch of strings, and numbers is going to hold a bunch of phone numbers per se. And so these are going to be the phone numbers for these particular people. But since they're strings and integers, they don't necessarily belong in the same list, but what we can do is create two different lists in which John's number is the very first index or very first number in the numbers list. So since he's the first element, his number is the first element. Rachel's the second element, her number is the second element. Ava's the third, there's the third, Steve is the fourth and last, and there's Steve's number. So this idea of parallel arrays kind of gives us the ability to kind of mix information of different types that all reference the same sort of object per se. It's not the only way of going about it. Next week we'll start talking about objects itself and how we can kind of encapsulate all of this data into one actual data type. But for now, this isn't a bad way of going about it. So let's just kind of see how that scripts up real quick and see if we can try that out. So let's go with a new Python file. I'll call it parallel array example. And let's do something similar to what was done in the note sheet there. Let's come up with a bunch of cities and maybe their associated zip codes. So let's talk about that for a sec. Let's come up with a main method real quick. So def main. And what I want to do in here is I'm going to come up with two lists, and at first they're going to have nothing in it because I'm just going to populate this list instead of hard coding stuff in it, so you can kind of see how we can populate these lists a little more clearly. So first I'm going to come up with towns, and I'm going to make this equal to an empty list to begin with, so it has nothing in it, but that way I can at least use the list methods upon it as I wish. And then we'll come up with zip codes, and that's going to be equal to an empty list. Now I'm going to call a function here that I haven't yet written, but I'm going to call a function that just says populate towns. And in this function, I'm going to pass in the towns and the zip codes. Okay. And then eventually what we'll do is just kind of print the two lists. Just so that we can see it's working. So now obviously this is wrong as it states right here. So let's come up here and let's actually make this function so we can use it. So I'm going to go def populate towns, and I'm going to pass in two things here. Since it's accepting two lists, I need to make sure I'm labeled to accept two things. So these things don't have to be called the same from parameter to argument, but sometimes it makes sense that it is. So I'll again call it towns and zip codes just to have it, and just to make sure we're working with lists. It's always kind of a nice idea in Python to kind of at least attempt to cast a data type to these so that when we use them, we come with the methods and PyCharm starts to populate those. So let's get into this. Let's first get a town name. So we'll go name equals input, enter a town name, or quit. Okay. And then we'll say something like while name is not equal to quit. Okay. What I want to do is then get the associated zip code. So we might do something like zip equals int input put enter the zip code, and then we'll start to populate that list. So we're going to go towns dot append name, right? Because that's the name of the town, and then we'll do zip codes dot append zip. Okay, and then in this loop I need to make sure I get another name so that I can get out of it eventually. So we'll just do this line of code one more time, and that should allow us to populate a list until I at least press quit. So let's call the main method here real quick. So we'll do this real fast. If name equals main, we'll call the main method. Whoops. And let's run it and see what happens. Whoops, what just happened? Get rid of that. Right click, run. Okay, so enter a town or name to quit. I'm going to enter a Lockport, and our zip code is 60441. Okay, I'm going to enter Tinley Park, zip code of 60477. Maybe we'll enter a town of Plainfield, 60586, and then I'm going to say quit, and that'll be it. And so once it's quitted, or we quit, the populate towns function has ceased, and therefore it kind of prints out what I did. Now, the reason I did this and had these declared in here and not as global variables, because I wanted to illustrate the mutability of lists. When we pass in lists by parameter, we're passing in the memory address for where the list is, and we do have the ability to manipulate the deeper values held within the actual elements. So we can add to it, we can remove from it, we can search it, we can sort it, we can do whatever we want with it when we grab it in through another function. So we don't have to be global variables in this sense when we're talking about lists. We can actually change the data within them just by passing them by parameter. Okay, so there's kind of an association with the zip codes. Now, oftentimes we'll want to be able to display them in a better manner than just the block, so maybe I'll come up with a function like display towns. Okay, and again, I'll pass in the two lists, so I'll go towns, and which is a list, and zip codes, which is another list. Alright, so to print this maybe a little bit more nicely, we could do something like print, maybe something like town, and we'll throw in a couple spaces, and we'll go zip code. And really what I want to do is now loop through the lists that I have. So I'll do something like this. Maybe I'll go for I in range, and I want to go all the way up to the length of one of these two lists. Doesn't matter which one, because they should have the same number of elements. So I'll go len of towns. Okay. And so what that's going to do is going to generate a sequence of integers from 0 up to, but not including the length of town. So if it has 3 elements, it'll give me 0, 1, and 2, and that's going to be the value of I as we go through. And now I can start to print some stuff in a more meaningful fashion. So I can go print, and I can do something like towns at I, and then we will also put a couple spaces in there. Oops. Just to spread it out. And then we'll also include zip codes at I. We're going to use the same location because they're in parallel. Index 0 of towns is the zip code from index 0 in zip codes. Right? So now instead of saying print here, let's hit display towns. And we'll pass in towns and zip codes. And let's see how that works. Right? So again, I'll have to populate the list first. So we'll do something like, again, we'll do Lockport 60441. We'll do Tinley Park 60477. We'll do Plainfield 60586 and quit. And now you can see that it prints in a little bit nicer of fashion. I could probably shorten this up a little bit so we don't have as many spaces and fill it out. But we've got a pretty nice setup here. You can kind of see how we've got things in kind of a column, a way of doing it. So that's just one way that we can kind of pass in and access things. Parallel arrays don't just have to be 2 arrays. You can have 3 arrays in parallel or more. It's just the indices have to reference the same sort or the same basic piece of information or object, I should say, that has these particular attributes. Okay, so there's an example of parallel arrays. Okay, again, we'll come up with some other ways of dealing with that type of information again, but this is a nice, efficient manner of going about it. Okay. Now the other structure I want to talk about are what we call two-dimensional arrays. So two-dimensional arrays are structures that can be processed similar to like a spreadsheet or a matrix. The visualization of such will always be where we think of it having rows and columns. So in this particular matrix or list would have 3 rows and 2 columns, and each cell is indexed accordingly. This is cell 0, 0 for row 0, column 0. This is cell 0, 1 for row 0, column 1. This would be cell 1, 0, 1, 1, 2, 0, 2, 1. But when we actually do it in code, we may visualize it that way, but really what it actually is in memory is a list of other lists. So that we have this list, and the data type held within this overall major list are lists themselves, and that happens to be a data type that we can use, and as long as it's consistent, it doesn't break the rules of an array. So here we have a list here that says 2, 4, and there's your first row. Here's the second row, 9, 4. Okay, and the third row 5, 6, or I should say row 0, row 1, and row 2. So building a two-dimensional array is kind of fascinating that we can play with. So let's kind of jump over to a quick example of a 2D array, and we'll show you how to build it. Now I'm not going to populate one per se, but I'll show you how you can iterate over it kind of quickly and efficiently. 2D array example. Okay. So let's do this. So I'm going to come up with the function def main, right? And in the main, I'm just going to generate a two-dimensional list like right off the bat. So we'll call it like arr2d. And that's going to be equal to a list that has other lists in it. Now sometimes it's convenient to write it out in this manner. So we might write something like this, and we'll kind of enter that over. Now let's do it this way. Once we hit a comma in there, it'll tab over nicely. Okay, so here we might put in a couple numbers like 3, 2, and 1, and then we'll put in some other things. Actually, let's back that up. And then we'll go with 6, 5, and 8, and then maybe a 3, 3, 1, and 2. We'll do 1 and 2, and then we'll do one more with so the list 9, 8, 7. Okay. Now generally you'll have it where it's rectangular in shape, where there's every column has the same number of rows at the very least. Sometimes they'll be square. You usually won't have arrays that will be called ragged arrays, where the values in each row have a different number of columns. It doesn't say mean you can't do it. It's just unusual to have such a thing. So let's do this. Let's find a way to display it. So just to print it out in a matrix style fashion. So how to display matrix. Okay. And in there we're going to pass in arr2d. Okay. So let's run this real quick, or not run this, let's make that function def display matrix. And here we're going to pass in an array. Okay, and we'll call it a list because that's what it is. It's a list. It's, yes, considered to be two-dimensional, but really it's a list of lists, so we just have the array that we're passing in. And what we want to do is kind of iterate through each row and column. So what we do is we have this nested looping structure that allows us to do so. So I might do something like this: for row in ARR. ARR is the two-dimensional list, and every element in ARR is another list, which I'm going to call row. Okay, and then I can iterate over each row and pull out an element. And then I can simply print it if I wish. So print element, and I'm also going to do this, end equals, and I'm going to put a space in there. And now once I'm done printing every element in a given row, I'd like to print a blank line of text so that I can get a new row in to start printing over all of those columns. Let's go ahead and try this out and see how it works. So we will run our main method, So if name is main, run the main. Okay. We'll run it, and you'll see that it prints out in a nice rectangular fashion, which is kind of neat. Okay, easy enough way to do it. Now you can use any looping structure you want as long as you can maintain the values of the indices and things like that. But we find that the for loop, especially in Python, makes a very clean, very nice way of building and maintaining the display and the number of rows and columns that we have to work with. Okay. So why don't we try, this is again, how do you process it? So here we have our values, could be a 3x4 array. Okay, in pseudocode we would declare it as such. In Python we just build them dynamically based on size. But either way, you'll notice that in a two-dimensional representation, this is row 0, row 1, row 2, column 0, column 1, column 2, column 3, and the indices go as such. Okay, we can always access any one element of a two-dimensional array very, very easily by simply just accessing it by indices. So we could just simply print, if I take out the display part, ARR2D at a given location, say 2, 1. So if I think about that, that's saying go to row 2, column 1, or go to the second element in the major array, or the second index in the major array, and the first index in that subarray. So if this is index 0, 1, 2, this is the array, the list that I'm looking at here, and I want to go to the first index there. So it should print this 1. So let's run it and see that that happens. And it does. And if I were to flip-flop this, say 0, 2, okay, here's element 0 of the major array. Here's element 2 or index 2 of the minor array. Okay, so again, I get another 1. If I wanted to go to the very last element, okay, I could go to, what is it, 0, 1, 2, 3, 2, and it should print the 7, and it does. And so processing it by index is also pretty easy to do. Okay. So let's get into at least one problem where it's kind of a bigger deal, more lab-like for a two-dimensional array. What we can create here, and I kind of like this problem, is what we call a magic square. If you've never heard of a magic square before, a magic square is a matrix or a two-dimensional array that's full of integers in which the rows, columns, and the two main diagonals always sum to the same value. So if I'm looking at a 3 by 3, you'll notice 8 plus 1 makes 9, plus 6 makes 15. 3 plus 5 makes 8, plus 7 makes 15. 4 plus 9 plus 2 makes 15. 8, 3, and 4, 15. 1, 5, 9, 15. 6, 7, 2, again, 15. And if you go down the diagonals, you'll find that it's 15 as well, whether you go down into the right or down into the left. Okay. We're going to make sure that the size is odd, and it should work out the same way. Now, the actual process of filling it is kind of interesting. Okay. When we do this, we fill it by placing the first number, number 1, in the top row center column. And then we attempt to move up and over to put the next element. Okay? If I move up and over and end outside of the range of the matrix, I need to either move all the way down or all the way to the left, depending on where I'm out of bounds. So for instance, if I'm trying to make the 1 here, I want to move up and over. Since I'm out of bounds on top, I move all the way down. Here's my 2. Then I move up and over, and since I'm out of bounds here, I'm going to move all the way to the 3. Now if I move up and over again, there's already a number there, okay? Which means instead I'm going to move down. And the trick to knowing this is that this number here, 3, 6, 9, they're all going to be factors of the overall size of the matrix. If this matrix has 9 elements, 3 is a factor of 9, 9 is divisible by 3, 9 is divisible by, or it's a multiple of 3, 9 is a multiple of 3, and so on and so forth. Same thing in the 5 by 5 case. If I hit a multiple of 5, I move down. So you'll notice I move up and over on the 1, down to the 2, 3, 4, 5. 5's a multiple of size, so 5 by 5. So I can move down 6, 7, 8, 9, 10. 10's a multiple of size, move down. 11, 12, 13, 14, 15. 15's a multiple of size, so move down, and so on and so forth. So It's a bit of a process, but let's go through it. I think it's a fun problem to code so you can see different ways of traversing arrays and things of that nature. So I'm going to scroll over here, and I'm going to make a magic square. Oops, not a Jupyter Notebook, but a magic Python array. Okay. So here's the deal. In thinking about this magic square, I always like to start with the main method because then I can start thinking in abstractions. Okay. And in the main method, I'm going to need to know how big this matrix is going to be, and I need to make sure that it's odd in size and not even. So let's grab the size that we'd like it to be. So int input, enter a size for the square. Okay, making sure that it's odd in value. Now, while size mod 2 is not equal to 1, okay, which means what I entered was not odd, okay, but even instead, I want to make sure I grab another size, okay, so I'm not letting the user type in improper data. It's just not going to happen, okay. So now that I have the size set up, I should be able to populate a magic square. And a magic square is simply an array or a list, so we'll make it a list, okay. And what I'd like to be able to do is first build it with nothing but zeros inside, so I have elements that I can manipulate. So we'll say something like build square, and I'll pass in magic square, okay. Then I'm going to want to actually populate it with all of the information that I want. I'm also going to pass in size here so I know how big to make it. So I'm going to populate square. And we're going to type in the magic square here. No need for size because we've already built it and it's already got the right size. And then I should be able to display the square. Okay. And again, we'll bring in the magic square so we can display it. Okay. Now, just because I have these listed out in this order doesn't mean I have to do them in this order. Let's actually take care of the display first, because then we can see what we're doing and making sure that it's being done correctly. So, and we already know how to do the display. It's pretty easy. Def display square. We're passing in a magic, we'll call it, which is a list. Okay. So let's just iterate over all the rows and make sure we're pulling out the elements. So let's go for row in magic, since it's a two-dimensional list, and for element in row, we want to print out its value. Now, the one thing that I'm going to want to do though is if there are two-digit numbers in there, I want to make sure that everything lines up correctly. So if there are any, if I have a size that would require two-digit numbers, those one-digit numbers, like 1 through 9, I'd like to make sure they have 2 digits, so like a leading 0. So I'm going to ask myself if element is less than 10, what I'm going to want to print instead is a 0 plus the string version of element. Okay? Again, followed by an end equals space. Okay? Otherwise, I'm just going to want to print the element, okay? So else print, and we'll do end equals space. Okay, so that'll allow me to kind of print everything, and once I'm done with a row, I want to print a blank line so that I get that. Okay, so let's kind of just come in here real quick. We'll just comment these out. It's worth testing anything we do. So let's just assume magic square had a couple elements in it, like a bunch of zeros. So we'll go 0, 0. Well, let's throw in a couple numbers here. We'll go 1, 13, and then we'll do comma 14 or 34, comma 9, and that should be enough just to test. Okay, so let's make sure we call the main method. and let's see what happens. Okay, enter the size. It doesn't mean anything for me right now, but at least it prints, and it printed appropriately. Any single digit numbers printed with 2 digits, and I got this nice square pattern, which is kind of nice. Okay, so I'm going to take these out because I don't really need them. Okay, we're going to actually fill that with stuff as we go. So let's right now focus on building the square. Okay, let's write that function. And for that, I need the magic, which is a list, and I'll need the size, which is an integer value. Okay. So what am I going to do here? Well, I need to make sure that I can build rows of the appropriate size and make sure I get the appropriate number of rows throughout there. So let's think about this. So we've got the size value that's coming in, and that size is telling me how many columns there are and how many rows there are. So let's go through a loop that will loop through size times. So we'll do something like for j in range of size. Okay. Now when I'm in here, I want to make a row, which is a list. That's completely empty as right now, and what I'd like to do is populate that row with elements like 0. Okay, so for, we'll go I in range of size again. And so what I want to do is go row.append, just simply a 0. Okay, just put something in there so that I can have a placeholder that I can index to later, because without it I don't have elements in there and it's kind of hard to work with. And once we're done building an entire row, let's put that row into magic. Alright, so let's try this. Let's build square and display square. Okay, so whoops, close that. Let's run it. And it says enter a size, so if I enter 3, it should display a 3 by 3 list of all zeros, which it did. 0, 0, 0, 0, 0, 0, blah, 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 blah. Let's try it again with maybe a different size. We can do like a size of 7. And there I go. I got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 7 rows, 7 columns, all filled up with zeros. Last thing I'm going to want to do to make sure I make this magic square is now fill it in and populate it with all the numbers that I want. So I want to put a 1 here, then a 2 down here, and a 3 here, and a 4 here, and a 5 over here, and then a 6, and a 7, and then finally an 8 below. Okay, so this is where things get a little bit more complicated, but if we start thinking about what we really need to do, it shouldn't be too bad. So populate square is what we called it, and we're passing in magic again, right? Which is a list. Just make it easy on ourselves. Okay, so here's the deal. I need to know how big this is, okay? So let's come up with a size attribute, and we'll say it's the len of magic. Now that'll tell me how many rows there are, but since it's square, it'll also tell me how many columns there are, so now I know exactly how big it is. I want to find out exactly where to put the first element, so I'm going to come up with a row value. I'm going to set it equal to 0, and a column value, and I'm going to set that equal to size divided by 2. So what that's going to do here is, since size, let's say it's 7, okay, based on the 7 by 7, I want to put the first element exactly in the middle here. Well, row 0, that's row 0, and size 7 divided by 2 makes 3. If I do the double slash, remember it's not 3.5, but just a straight 3. Well, this so happens to be index 0, 1, 2, 3, the exact middle. So as soon as I cut it in half, I'm going to get the exact middle of where I want. And what I want to do is put a 1 there. Absolutely. So I'm going to go magic.append. Not magic.append. I want to go magic at row col, and I want to set that equal to a 1 right off the bat. Okay. Now I know that's not everything, but let's run it and just make sure it works. And I'll enter, say, a 7 by 7, and you'll notice that that center column, first row, came out with a 1, which is really kind of neat. And so now my goal is to try to fill up the rest of them based upon how big it is. Obviously, that's going to have to be some sort of looping activity. Okay. Now, the looping activity is not going to be based on rows and columns because the pattern is kind of, let's just say there isn't much of a pattern for how it goes in. It's a little obscure. So let's loop through all of the elements that I have to place, and then we'll figure out where to place them and how to move the row and column values. So what I'm going to do is come up with a for loop here. That's going to go I in, well, let's call it next number actually, in range. And we're going to start this at 2 because we've already placed the 1, makes sense. And we're going to go to size squared. I'm going to go +1. Now, size squared is going to be 7 times 7, or 5 times 5, or 3 times 3, and that's going to tell me how many elements there are. Now, the reason I go the +1 is because notice that when I use the range function, that number is never actually included. I want to make sure it's included so that I can get the actual 49 in there if we have 7 by 7 size. Okay? So now the pattern. The trick is to move up and over, and if we're out of bounds, move it to the appropriate place. So if my row becomes negative, move it to the bottom row. If my column becomes too much, move it to the first column. So up and over, up and over, up and over, unless, of course, the number we would like to place, or the number we previously placed, happened to be a multiple of size. Since that seems to be the most restrictive piece of information, it's actually the one I'm going to take care of first. So I'm going to say something like this. If next number -1, because that happens to be the number that I just put in the matrix, next number represents the number I'd like to place in there next, but I want to know what happened just before that. If next number mod size is equal to 0, I want to make sure that I move the row down 1. So I want to increase the row. And that's it. I don't want to do anything else. Okay? Now, if that's not true, then I want to try to move up and over. So move the row up, so -1 from it. And move the column to the right, so increase the column by 1. Okay? So either way, when I do these manipulations, it is possible for me to get out of bounds. The row can become negative, which we know we can't use, and the column can become equal to the size, which again, we know we can't use. So I do have to kind of ask myself a couple more questions here, saying if, say, the row is less than 0, if it's negative, okay, then set the row equal to size -1. Okay. What that'll do is put it into the last row of the thing. So if it's 7 by 7, size is 7, -1 makes 6. That happens to be the last row of the matrix, index-wise. Same thing with the column. If the column is greater than or equal to the size, I'd like to move the column all the way back to 0. And now that I know exactly where to place the element, I need to put the element in there. So we're going to go magic at row col equals next number. Okay, so let's see if that actually works. So we know that this part worked no problem when we populated it. Now we're kind of testing this. So we're supposed to go through all the numbers 2 up to size squared. If the number I just put in prior to the one I'm looking to put in, if that happens to be a multiple of size, move the row down 1. Otherwise, try to move the row up and the column over to the right. If either one of those values becomes an issue, goes out of bounds, then put it in the right spot, and then finally set the number, the next number, into the appropriate place. So we've already got this uncommented. Might as well give it a shot. And we can enter the size. Let's go 3 by 3. And here, 1, 2, 3 to the right, or to the left. 3 is a multiple of size, so down 4, 5, 6, a multiple of size, down 7, up and over, so move all the way here. 8, up and over, move all the way down. 9, and we have our magic square. We could try it again with something bigger if we wanted, 5 by 5 or 7 by 7, and it still works. 1's dead center, up and over, 2, 3, 4, up and over, go all the way, 5, 6, 7, multiple of size, so move down. 8, 9, 10, up and over, 11, 12, up and over, 13, 14, multiple of size, 15, 16, 17, 18, 19, and so on and so forth. So two-dimensional arrays are kind of a neat little data structure. It allows you to kind of organize things into a nice kind of row and column format. You can use this for all sorts of applications. I like the magic square problem simply because it gives you a flavor of iterating over things in a couple different ways. So one, it shows you that you can still display the elements using those nested for loops. Okay. It also shows that you can build a two-dimensional array using those nested for loops, but you first have to make sure that you populate an entire row and append that entire row to the overall piece. Then you want to populate the entire square. This is where things get a little bit abstract. You want to make sure that you, in this particular instance, we couldn't just iterate over the rows and columns because we had to place everything in a very specific spot. So what I do is I keep track of where I'd like to place it, I figure out where that's going to be, and I set it in so now you can see us actually manipulating the values within and assigning it. So it kind of gives you a flavor of everything that you can do with the two-dimensional array in terms of populating it and displaying it. Right? And again, with all of the methods that you have and all the tactics you have of just arrays and lists in general, you can still apply to two-dimensional arrays. You just have to know what you're pulling from and how you're working with it. Anytime you're using this double bracket notation, this first set of brackets would happen to be an entire list that's within the major list. And the second set is just simply an index for that sub list that you're looking for. So hopefully that kind of helps with the different types of data structures. So you've got one-dimensional arrays, static arrays, which we call lists. You've got parallel arrays, which means you can have different types of information in different arrays that all correlate somehow based on index. And then finally two-dimensional arrays if you have something you want to store in a gridded format or however that may be. Maybe it's a seating chart for a classroom or boarding passes for an airline, or maybe it's a menu and different prices per item and things of that nature. So you've got all sorts of options for these data structures. You just have to figure out what's appropriate for your situation and use it. So hopefully that clears some things up. The lab that you're going to be working on this week is just going to deal with a one-dimensional list, not a two-dimensional list, but you do need to make sure you're comfortable with the two-dimensional structure for later on. If you have any questions regarding the examples, which I will post on Blackboard, or the lab itself, feel free to post those in the discussion thread in Module 7, and that way we can discuss them and talk about them so everybody can see. So hopefully that kind of clears things up, and you're able to progress a little bit through the lab and the quiz. Let me know if there's any issues, and I will see you in the next module.